that I can guarantee via this extreme value theorem, which I'm not going to prove, that there is even a maximum or minimum. All right, so step one is I'm going to focus my attention on continuous functions on closed intervals. All right, so now look at these three pictures, and can you like say something about the extrema, the max and the min? What are all the possible, this is not a deep question, what are all the possible places where I should look for maxima and minima? And by that I mean absolute maxima and minima. Sydney. Curves and stuff. No, like specifically. Where should I look? Here's a function. Here's a function. Here's a function. If my goal would be to find out where this function is biggest and smallest, where is this function biggest and smallest, and where is this function biggest and smallest on these intervals? Where should I be looking for such things? What? Beginning and end, yeah, okay. So that's one answer. I should definitely look at the beginning and end because as we've seen, look, it turns out that the minimum of this function on this interval is that one, right? And the maximum of this function on this interval is that one. And here the minimum is here. And here that's it. Okay, so does everyone see that I definitely have to check the endpoints? Okay, so big thing I learned number one is examine the endpoints of the interval. Or else should I check? Okay, he says where the derivative is zero. Can I get an answer that's actually not in calculus language? It's actually just such a boring answer. It's like not even almost worth saying. Yeah, Pearsma.
Change direction because
yeah, or no, this is like actually this is like a borderline like a dumb question. Like yeah, or
where the tangent line is zero.
yeah, you guys are all trying to do like math. I'm just like saying I'm actually like stating like an incredibly obvious thing. I need to look.
I said curves and stuff.
Then, so a little bit more than that. So I need to check the endpoints or
between
or relative extrema. That's all right. Or relative. All right. That's basically it. The answer is, look, man. If I need to find where the function is biggest, that's either going to happen at the endpoint, or it's going to happen at a relative max or relative min. Does everyone feel that that's like exhaustive? All right. So okay. So Stephen, I'm gonna just keep talking to you. I don't know why, because you never say anything back. So it's a perfect dialogue.
It's like the opposite of dialogue.
I know, it's a joke. Stephen, overall goal is find the max and the min. And thus, this really boils down to two separate tasks. Task 1, check the endpoints. Task 2, find the relative max and relative min. Okay? And then, once I find the relative max and relative min, I just need to check and see, like, yo, which one has the biggest y value, the endpoint or the relative max or min. Alright, so basically, this is the big conclusion of the last half an hour. 2, find extreme.
Oh yeah, Mr. Rose, we
up?
have 20 minutes left of SD card space.
Shut up. Really?
Yeah, that's what it says.
Okay, alright, to find extrema, where do we need to look? We need to look at endpoints.
It's right there.
Endpoints. Look at the endpoints. We need to look at relative extrema. And then we need to compare them. Do you agree? This is essentially our algorithm. It's not even an algorithm. It's like just a boring statement of the obvious. Find endpoints, find relative extrema, compare them. Okay, how do we find relative extrema? All right, now comes all this crap you guys were trying to say 3 minutes ago. Where do I find relative extrema?
When the derivative equals 0.
When the derivative is 0.
But also the derivative should probably go from like positive to...
Okay, wait, anything else? Good. Why is he saying when the derivative is 0? I think we probably talked about this once, right? The answer is just duh. See what, you stop talking, you stop talking? So, why is Calvin saying look when the derivative is 0? Because duh, look at this picture. When the derivative is 0, doesn't that, this beautiful picture, does it not appear that there are relative maxima and relative minima when the derivative is 0? Yeah. Eric, it's so great. Whenever the derivative is 0, you have a relative max or min. Whenever there's a relative max or min, the derivative is 0. Life is wonderful. Dun 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 dun. No, life is not wonderful. Life is misery and pain. Then it's over. Just kidding.
Are you okay?
I'm fine. Well, I don't feel so
there's
good,
a whole team of counselors down there.
Actually, life's pretty much fun. All right. This is the best one yet. Okay. It turns out that it is not quite true that there is this exact correspondence between places where the derivative is 0 and places where there are relative extrema. Okay. So now comes thinking time. You should stop giving away all the secrets. What I would like you to do is two things. One, I'm going to say them out loud and I'm going to write these down also. Find a function such that the derivative is 0 at a particular point. And don't say anything. Don't give it away. Find a function where the derivative is 0, yet there is not a relative max or min there. Next, find a function in which there is a relative max or min, yet the derivative is not 0. Go.
Wait, what? Say it again?
No, I'm going to write it.
Okay.
Yup. Yeah. A flat line doesn't work because actually, based on our definition of relative max, this is kind of weird, and sorry if it's going to upset you, but if you give me a flat line, f of x equals 2, for example, then there is a relative max at every single point. Because every single point, it's like, yeah, it's like communism. We're all equal, so we're all the best one nearby.
Scott, what's the U value? What do you say about that? Yeah, but what is more equal than 1 to shake his head?
I'm not doing that. Draw a picture. Hieroglyphics and? Yeah, okay, good.
What?
Okay, explain to your table.
Wait, are you saying like?
So does f have to be continuous? Does f have to be continuous?
Nope. But it's possible to draw it. There are continuous examples. There are counterexamples that are continuous. All right, what do you got for this first one? I saw it on a lot of papers, like at least one from each table of the tables I visited.
Like x cubed one of them.
Exactly. Yeah, x cubed. Classic function f of x equals x cubed. What does it look like? It has the subtle curvature that we keep talking about all the way since pre-calc A, and sure enough, there is a tangent line here. This freaks out some students because, like, Gabe, for example, is like very upset that a tangent line can cut through the function. I had a long conversation with him about this. But nonetheless, it is a tangent line. The derivative is 0. There's a horizontal tangent there. If you don't believe me, you know, we can just like take the derivative. It's 3x squared. And this is not really convincing if you're not already convinced. But the derivative is 0 there. So this function has a horizontal tangent. So unfortunately, here's a function where the derivative is 0, yet there is no relative max or relative min here. Does everyone see that? Okay. And so Busa said a thing. Maybe you can say it again now. What? So I got maybe or not. So what I learned from this is just because the derivative is 0, it's not necessarily true that there's a relative max or min.
But most times.
Most times or something. Often. Yeah.
Very often.
Very often when the derivative is 0, there's a relative max or min, but not necessarily, okay? So actually, so she's saying something important, which is the places where that if we want to find the relative maxima and minima, and we do, then we should check the places where the derivative is 0, and then some of them might be relative maximums and others not. Okay, unfortunately, it's also not true that when you have a relative maximum, the derivative will be 0. Can I get a counterexample?
Absolute value.
Yes. Some kind of like upside down absolute value type thing, right? If this function is pointy here, then aha, you say, I'm cheating, and I am kind of. This function is not differentiable here at x equals a. Yet it is certainly a relative max by all of our normal definitions of relative max. Okay, so this is actually terrible. Yes, Busa.
I think I know what you wanted to say.
You think I know? Oh, I don't know. It doesn't matter. We'll move on. And so, guys, this is. Do you see how this is kind of annoying? Because not only is it not true that when the derivative is 0, there's a relative max, but it's also not true that I can find all the relative maxes by just looking when the derivative is 0. All right. So, however, what did we have to do to construct that second counterexample? We had to kind of get like a little ugly about things, right? What got ugly?
Well, the derivative kind of changed signs, even though it was never really 0.
Okay, someone else. More things. What did I have to do? What terrible thing did I have to do to make that second counterexample work? Yes, you should say it again.
To make it undifferentiable.
Yeah, this function is actually just not differentiable here at all. So it's kind of a little bit cheating, right? Because I told you guys don't feel cheated, or maybe you're just following all inside. But yeah, I said find a function where the derivative is not 0. Well, here the derivative is not 0 because the derivative just doesn't exist at all. All right, so what I think is true is that if the derivative does exist and there is a relative max, then the derivative must be 0. And there is a name for this. It is called Fermat's 0.
For who?
Here.
French word, Fermat.
Wait, what?
Okay.
I missed it.
Fermat is one of the I'm pretty sure, if I get this wrong, it's going to be really embarrassing, but I think he was in the generation before Newton. True? Someone look that up in
He was
their
born in
phone.
1601.
His
No,
stuff
in
like
the
very late
65.
I think he did stuff before Newton. I think he was, I think,
Born in 16.
I think he did some like, kind of, anyway, I'm not really sure about that though. He's one of the people credited with Descartes in kind of sort of popularizing coordinate geometry, which made all this possible. Anyway, moving on. Here's what Fermat's theorem says. It says, if f has a relative max at x equals c. So first of all, I'm insisting that there be a relative max, or min, but I'll just state it for max. And f prime of c exists, then what? If there's a relative max, and the function is differentiable there, Use your imagination. Calvin's got it already. What can I say? What's 0? The derivative is 0. Is that what you're going to say, Calvin?
Yeah.
Yeah.
Can you say this talking about slopes because, or how do you say this without calculus?
How do I say this without calculus?
Yeah.
I don't. It's a calculus theorem.
I thought it was in Newton.
What?
I thought Newton invented calculus.
Yeah, but there were bits and pieces floating around. I'm not really sure. I'm sorry. I'm not a historian. I just pretend to be one. Not. Okay. Yo.
So I'm just assuming it has to be that C is not one of the endpoints. So it's weird.
Well, if it's a relative max, then I've already committed to it being a relative max, so it can't be one of the endpoints. Relative max. Relative max. If f has a relative max at x equals c, and the derivative exists, then the derivative is 0. Okay, let's prove this right now. This is a classic case of a proof which mostly writes itself. If you just kind of start writing things down, suddenly you're just like one line from being done. Alright, so let's see if I've caught you anything. How should I begin? How should I prove this?
Assume the constant, the antecedent. You know, the thing you always say.
The thing I always say, yeah, good. How did you predict that the thing I was going to say is the thing I always say? Yeah, this is a conditional. This theorem, like almost all theorems of mathematics, is in the form if some crap, then some crap. And so the way you prove a conditional is you assume the antecedent and you derive the consequence. That is very correct. And so we will assume two things. What are the two things we're assuming?
F has a relative max at x.
Yes, f has a relative max at x equals c. That's one assumption. And my second assumption.
The derivative of f at c is not equal to 0.
No, it's 0.
Oh.
Oh, no.
not
Just that it exists.
Yeah, just that.
Yeah, just that it exists. Yep. So on those two assumptions only, there is a relative max at x equals c and f prime of c exists. And now what I need to do is, somewhere down here, I need to prove what?
I mean, say that the derivative of f of c is not equal to 0, then show that that can't happen.
Okay, that's a way. You're saying do it by contradictions, but I'm saying like, okay, the overall goal is just to show that it's 0. Alright, so how can we do this? Alright, this is one of those cases in which I think it makes sense to start writing out all the things that you know and writing out all the things that you want and then just like match. So what does it mean if f has a relative max at x equals c? What's the definition of relative max? Kendall.
The relative max is for a substantial beginning that its size.
Closed interval.
Sorry.
Wait, you can stop talking. Kendall again. Because I kind of wasn't listening and also interrupted you.
FC is a relative maximum if on an open interval containing C. I'm just going to read it. I have it right here.
All right. Yeah. If on some open interval, it's the largest, right? Basically, this has to be the biggest. Okay, so let's just kind of just beneath that, I'm going to sort of rewrite that. So what does it mean if f has a relative max? What it means is, maybe I'll just be kind of even loose a little bit. I'll just say nearby C. What's true is that what?
F of C is the biggest.
F of C is the biggest. That f of c is greater than or equal to f of x. Okay? That's just kind of like a restatement of what it means, of what that means. All right, what does it mean if f prime of c exists?
Wait. So isn't nearby like a little range?
Nearby? If you want me to be more technical, I don't feel like it because I've already moved on. It's just like there exists some open intervals such that within that open interval.
Just like relative max in general, just like.
Wait, hold on. Moving on. The derivative exists. How do we show? What does it mean? What does it mean that the derivative exists?
There's a tangent.
Okay, it has to be continuous. That's true.
Oh, the limit doesn't go from one side. Like, the limit just goes from the other side.
Okay, he's mumbling something about limits.
There's a tangent line.
What exists?
The tangent.
Yes, Emma is reminding us that the derivative just is a limit, right? And so if we say that this derivative exists, then we're saying that some limit exists. Scott, what limit, what is f prime of c? Like write it out in limit form. We get down into like the,
Just like the definition.
yeah.
Well, so f of c plus h minus f of c over h, the limit as h approaches 0.
That's perfectly correct, although it's more convenient if we use the other one.
So like f of c minus f of a over c minus a as c approaches a.
Yeah, okay, but I think you're basically right, but I think you sort of switched the letter. What I want is, I want the variable to be the other one. I want it to be getting closer to c. So it's like the limit as x goes to c of
f of c. Yes.
Let's do it the other way.
Minus x.
But but what you said is also fine. So yeah, that. Stop paying attention. Excellent. Cool. Okay, that is by definition just f prime of c. All right, so this limit exists. All right, so okay, I'm trying to kind of like walk you guys through like sort of proof strategy. And the general proof strategy, at least for these kind of boring proofs, is yo, write down this thing that I know, write down this thing that I know. So I know that f of c is larger than f of x, and I also know that this limit exists. And what should my goal down here is to prove that the derivative is 0. In other words, prove what? What do I need to show?
That if that and that, then the derivative of f of c is 0.
Yes, he's saying, hey man, you just told me that you just reminded me that the derivative is a limit. In other words, what I really need to do is show that this limit is 0. Okay, so this is, now I'm feeling pretty good because now I've got it down to,
You have
yo,
2 minutes.
what's up?
You have like 2 minutes.
I have 10 minutes.
2 minutes on this.
Oh, I have 2 minutes of the camera? Whatever.
You don't get to see the core.
Yeah, we'll miss it. I'll pick it up tomorrow. I don't know, do something. All right, so I'll like instantly. I already did this one. I like sort of did a fade out after this class. The ninth period just kind of like came in suddenly. I was like, Bushis, say something about the cone, and then it just immediately switches to like a different class where they're like talking about the same problem. And I was rushing them less. All right, so I'll do that again. Show that this limit is 0. How can we do that? So that f of x equals f of c. Yeah, okay. I don't think it's going to be so easy though. Anyone notice anything about this limit that I can say for sure? Okay, so please, you need to do 2 things right now. You need to keep your eye on the prize, which is proving this statement, and you also need to keep your eye on your tools, which are these 2 facts. So I know this limit exists, and I need to show that the limit is 0, and I also know this other weird thing. Okay, one of the 2 people in the Calvin Emma table, say something.
What? Oh, I guess you can sort of like replace the f of x with something that's less than f of c.
Yeah.
Like basically I'm just pointing like over there, you already know that f of c will always be greater than equal to f of x. And over there you have like this helpful f of
Okay,
x.
she's talking really fast. Yo, summarize in like a few short words.
Top thingy is negative.
Top thingy is negative. Yes, that is the key insight, which is that
Or
since,
Or 0.
or possibly 0. Thank you, yes. F of x is greater than or equal to f of c. Since f of x is greater than or equal to f of c, that means that this numerator